Good morning, dear colleagues. It is my pleasure to present our work entitled Normal Regular Solutions of Hypergeometric Systems and Their Connection with Classical Functions. This research was carried out jointly with me, Meiramgul Talipova, and my colleagues Altınşah Pikpova and Galia Abdikalikova at Zhubanov University, Aktubi, Kazakhstan. In this work, we applied the Frobenius-Latышeva method to the Apple hypergeometric system F2, construct a fundamental system of normally regular solutions and establish connection with classical special functions. Let me begin a brief introduction and motivation for this study. Hypergeometric functions occupy an important place in the theory of special functions and mathematical physics. The fundamentals of the theory were laid by Euler, Gauss, Kramer, and Riemann. Later, the theory was extended to functions of several variables, leading to Apple, Horn, and Lauricelli hypergeometric systems. These systems arise naturally in mathematical physics, quantum mechanics, field theory, and algebraic geometry. The Frobenius-Latышeva method is a generalization of the classical Frobenius method for systems of partial differential equations. It allows us to determine characteristic exponents, to construct normal regular solutions, to study resonance cases, to obtain logarithmic solutions, and to establish connection with classical special functions. In this work, the method is applied to Apple system F2. It solvistics the system 1. It's solvistic the system 1. The system 1 has a regular singular point at the origin xy equals 0, 0. The solution of system 1 is called normal regular 0, 0 if it is representable next function 2, and the coefficient satisfies as a required scheme ensuring absolute convergence of the series. Substitution 2 into system 1 leads to characteristic equations rho and sigma, 3 and 4. From here, we obtain four types of indicators: rho 1, rho 2, sigma 1, and sigma 2. Therefore, four pairs of indicates are obtained. After substitution rho 2 into system 1, we obtained 5, 6. Solving the system of recurrence relation 5 and 6, we obtained formula 7, AMN. The next, you can show our main theorem 1. The first theorem states for each pair of indices 0, 0, these four pairs, there is a unique normal regular solution of the system 1 in the vicinity of the point 0, 0. The proof follows uniquences of coefficients obtained from recurrence relations and convergence of the resulting double series. Therefore, each pair of exponents generates exactly one normal regulation solutions. Then you can see 8 formulas and therefore 9 formulas. And the right side of the first equation takes 4x. It's you can show formula number 10. Comparing the coefficients at the same powers of x and y, we obtain the recurrence elevation, 11 formulas. Similarly, from the second equation of the system 8, we obtain the next formulas, 12 formulas. Definition in indices. Consider the coefficients and the smallest power x rho, y sigma. From the first equation of system 8, we obtained rho equals 0, since a 0, 0, no equals 0, then rho equals 0. Therefore, the two value rho 1 and rho 2. Similarly, from the second equation of system 8, sigma equals 0, whence sigma 1 equals 0, sigma 2 equals 1 minus C2. Thus, for pairs of indices, we obtained the next 13 formulas. Uniqueness of determination of coefficients. Let one of the pairs rho and sigma be fixed. Suppose that the system parameters satisfy the conditions C1, C2, so that determination is formulas 11 and 12 do not vanish. Then each coefficient a, m, n is uniquely determined through lower order coefficients. By sequentially applying recurrence relation, we obtain the next formula 14. Therefore, all coefficients of the series are completely determined by a single arbitrary factor a00. Now, let's start investigating the convergence of the series. Consider the ratio of adjacent coefficients. This formula at m to next formula, similarly this formula. Therefore, by the Horn criterion for double power series, the region of absolute convergence is determined by condition x plus y, it's all in modulus, less than 1. Thus, series 2 convergence in some neighborhood of the origin. For each pair of matrix from set 13, the series coefficients are determined recursively and unambiguously through A00. The corresponding double series converges in the vicinity of the point 0, 0. The third, the resulting solution is normal regular. Therefore, for each pair of includes, for pair rho and sigma, there is only one normal regular solution to the Apple F2 system. This theorem is fully proven. Solution representation via Apple function. For index rho equals sigma equals 0, we get the next solution, 15. The remaining solutions have the next formulas, 13, 17, 16, 17, and 18 formulas. The next theorem 2, the function y1, y2, y3, u1, u2, u3, and u4 corresponding to the indicators, the next 4 indicators, from a fundamental system of normal regular solutions of the Apple II hypergeometric system. And the next proof, let's introduce. According to the theorem 1, each pair of exponents corresponds to a single normal regular solutions. Subjects sigma C1 and C2, difference in the k figures are not integers. Therefore, functions U1, U2, U3, U4 have different principal members, and they are therefore linearly independent in the neighborhood of 0, 0. Since the rank of the hypergeometric Apple system is F2, for the number of linearly independent solutions found coincidence with the dimension of the space of local solution. Therefore, U1, U2, U3, and U4 form a fundamental system of normal regular solutions of the F2 system. This theorem is proven. The next theorem, theorem 3, with y equals 0, The Apple function f2 goes to enter hypergeometric Gaussian function 19. Therefore, the Gaussian hypergeometric function 19 is a special case of the normal regular solution of the Apple hypergeometric system f2. The next proof. By definition, the Apple function is f2 given by a double series, formula 20. When y equals 0, then we get the next formula, 21. As the next system 0, then all terms with n more than or equals 1 vanish. Therefore, only the terms corresponding to n equals 0 remain the next sum, formula 22. From the properties of the Pontchammer symbols follows B2 equals C2 and equals 1. Therefore, formula 22 takes the next formula 23. But the right-hand side, 20, is the definition of the Gaussian hypergeometric function. We have the next formula, 24. Comparing 20 and 21, we obtain the next formula, 25. Thus, it is proved that the Gauss function arises as a special case of the Apple function f2 when limited to the y equals 0 coordinate axis. This theorem is proven. The next, you can show example how these all methods we can to use. Consider the Apple function f2 by this definition. For example, path y equals 0, then by theorem 3, we have the next results. By definition of the Gaussian function, since the next means the next value, we get the next formulas. From the known formula, this when x less than 1 follows the next condition, therefore we have the next means. If let x equals 0.5, then for this formula, since for this logarithm, we get the next results. Let's check for a number, and in the total we have the next value. Conclusion for parameters that for special parameters value, the Apple function reduced to an elementary logarithmic functions. This clearly illustrated the connection between solution of the Apple system and classical special functions. To conclude our work, a fundamental system of normal regular solution of the Apple system f2 was constructed using the Frobenius-Latышeva method. Explicit recurrence relations for the coefficients were obtained. Representations through the Apple function f2 were established. Degenerate reductions to the Gauss hypergeometric function f2, f1 we investigated. Thank you for your attention.